Hi there, we are going to review Unit 1, Lesson 3 on isometry. We're going to skip over the warm-up to make sure that this video is not super long. You are going to need some patty paper. You're going to have to work on your own with the patty paper. It's just very hard to describe with the video, so my apologies. When we are looking at 1.3.2, an exploration of isometry. We have 5 frames here, and we have to kind of figure out what went on with these 5 frames. So if I look at frame 1 to frame 2, what happened there? You can pick out that what happened was that we had a slide to the right. What about 2 to 3? Well, when I look at frame 2, the polygon is concave pointing up, and then in 3 it looks like it's over to the side. So we had a turn, and that turn was to the right. From 3 to 4, the only thing that happened there is 3 is a little bit higher than 4, so we had a slide down. And 4 to 5, that polygon is located in the same corner, but it's opposite direction, so it's turned the other way. Okay. So again, you're just kind of recognizing what happened. Now, with number 2, I have a little note here that I want you to do this on your own. The instructions are pretty intense. Let me know if you need some help with it. But what you're discovering is you keep going back to the frames on number 1, and you're discovering slides, you're discovering rotations, and even reflections with your patty paper here. So I believe it's 3 sheets that you'll need. When you get done with that, and give yourself some time and practice, when you get done with that, you should be able to answer these questions right here. I went ahead and gave you the answers, so when you're playing around with the patty paper and you get to here, you'll know if you've been doing it right. Number 3, more patty paper that you're using over there. Once you get the figure rotated, or once you get the figure drawn, you're going to rotate it on this circular graph paper right here. So you'll put your drawing of your polygon, you'll center it about the origin, that point right there, and you're going to move it so it looks like frame 3. So what did frame 3 look like? There we go, there's frame 3. So how many degrees did you turn it to get there? So when you rotate it, you will rotate it 90 degrees clockwise, or if you went the other direction, that would be 270 degrees counterclockwise. The center of rotation is going to be the center of that polygon. Using the patty paper, a ruler, or a protractor, complete the table here. So we're going to complete the table by determining if the polygon changed size or shape as it moved. When you went from frame 1 to frame 2, did the size change? No, it didn't. What about the shape? No, it didn't. 2 to 3, no change in size, no change in shape. In fact, look at it, none of these had a change in size nor in shape. And what kind of tools did you use to determine if the size changed? You could have used your ruler if you wanted to, or you could have just used the patty paper. And I can't spell patty. Okay. What tools or information were used when you determined if the shape change. Same thing, patty paper. Okay. You could see that they mapped on top of each other. It looked like the original figure, nothing changed. So when you're thinking about it, I know it says discuss with your partner, but your partner is this video. Did the measurement of the angles in the polygon change from frame 1 all the way through to frame 5? No, they did not. So things that did change is the way that it was oriented, like it might have been sideways instead of up. It might have changed position on the paper, but the original figure did not change size, nor did it change shape. So we've got a lot of definitions here. This is probably one of the sections that have the most definitions. We have a reflection, and we use that word, we use flip to describe that word. A reflection is a type of transformation that gives us a mirror image of the geometric figure. So we still have the same figure, it's just pointing a different direction. A rotation is another transformation that will turn it about a point or an axis. And the amount of the rotation is in degrees. A translation is just a slide. It's moving every point of a figure the same direction and the same distance. So these are 3 of our 4 transformations. These are all transformations. An isometry is a collection of transformations. So an isometry is a transformation that preserves distance and angle measure. Again, a collection of transformations. So you may think of the term congruent to describe isometry. So we have some more definitions over here. A rigid transformation is a bunch of isometries. We are looking at translations, reflections, or rotations. Rigid means that they will not change. They're going to be all congruent. Sometimes we call a rigid transformation a rigid motion because it is moving. An isometry is comprised of rigid motions. Figures that are exactly the same shape and size, they are known as congruent. So when you're bored, go back and read some of these vocabulary terms again. Okay, so we've got a collaboration that we did in class, and I'm going to kind of walk you through it. It says we have a diagram, a polygon RTDH, R prime, T prime, D prime, and H prime. That's how we read the result when those little apostrophe looking things are there. The arrows that they have here highlighted in like this orange color are showing a possible path of a transformation. If I move every point up and over to the right, will it map on top of D prime, T prime, or I'm sorry, D prime, H prime, R prime, T prime? I might have said it out of order. Let me look at it right here. Okay, R prime, T prime, D prime, H prime. Sorry about that. Okay, so let's see how many units it went up. 1, 2, 3, 4, 5, 6, 7. So 7 units up. And 1, 2, 3, 4, 5, 6, 7 units to the right. Okay, so the question is asking, the arrows is a possible path of movement. If I move every single vertex, will it map on top of its corresponding vertex? Let's see, if I move T up 7 and then to the right 7, will it map over here? If you count it out, yes it does. If I go up 7 and to the right 7, okay, that will work. Let's try it with R. If I go up 7, I'm not even in the graph. So no, it doesn't work with R, and it's not going to work with H. So do all the points use the same path to get to that R prime, T prime, D prime, H prime? That answer is no. 2 of them do, but not all of them. Okay, let's take a look at number 2. Number 2 wants us to draw a line segment from point K to the purple line. Okay, there's K to the purple line. What is the length of that line segment? Well, if I count it, 1, 2, 3, 4, there's 5 units. Draw a line segment from point D prime to the purple line. That's also 5 units. So let's describe the relationship between the two. Well, both of those purple line segments are perpendicular to this purple line. Okay, so they're both perpendicular, and they are also the same distance away from the purple line. This is 5 units, this is 5 units. So it is equidistance, which brings us to our definition on the following page. That corresponding points have the same distance from a line, then that line is the line of reflection. So that purple line that we have there, this purple line right here, that is our line of reflection, because K is 5 units away from the line of reflection, D prime is 5 units away from the line of reflection. So K would reflect over that line and map onto D prime. For each of the other vertices, draw a new point using the same movements done to map D to K. Then show the reflection using the line segments. So let's go ahead and do that. I'm going to, looks like the path that they gave us looks like down 3, and then that looks like to the right, 1, 2, 3, 4, 5, 7. Okay, 7. So I'm going to do that with every single point, and let's see what happens. I'm going to kind of color code it. So we've already got K down there. Let's move T over. So if I go down 3 units, 1, 2, 3 over 7, 1, 2, 3, 4, 5, 6, 7. Okay, let's do R. We're going to do that in blue. Okay, so down 3, 1, 2, 3 over 7, 2, 3, 4, 5, 6, 7. There is the blue one. Let's see, H. Let's use brown. So we'll go down 3 units, 1, 2, 3 over 7. Okay, there we go. I'm going to go back and make sure that one's purple. All right, so now I'm going to draw my figure. Ah, look at that. I can reflect it over that line of reflection and it should work. Okay, so we drew a new point, then show the reflection using line segments. Okay. Describe the relationship each line segment has to the purple line. Both line segments are perpendicular. Oops, I'm sorry, I read the wrong question. Here we go. Discuss with your partner if the mapping of all the points on R, T, D, H can be done using the same path and reflection, or if only the mapping works for the vertices. Well, let's go back to that picture. The mapping worked for all of the vertices. We got to move everything over, then we can reflect, and that will give us R prime, T prime, D prime, H prime. So yes, all points can be mapped this way. All right, you are not going to get anything out of this lesson unless you play with the patty paper and give yourself some time to be able to do that. So yes, all points can be mapped this way. hope this was helpful, and I'll see you soon.